All right, what I want to do in this second to last video for the course is very briefly introduce the concept of bounded variation. This is typically a more advanced topic, and it's definitely a topic I'll talk about in my harmonic analysis course because it has really nice connections to the pointwise convergence of Fourier series. And when you do this topic in higher dimensions, this is a very deep kind of concept. I forget even the definition. I don't think it has a very simple definition for functions on, let's say, a cube in higher dimensions. Really, I mean, to be blunt, the reason why we're doing this is, well, it's on the prelim, so I mean, it is a very beautiful, useful concept in pure and applied math. So, the idea of bounded variation, total variation, that is actually extremely useful in data science, particularly in image processing and image reconstruction. Maybe we'll do that in the harmonic analysis course. But anyway, okay, so BV functions, BV for bounded variation. All right, so let's say we have a function real valued on a closed interval. So you really could have done this, and it really fits almost more in AMAT 511, but definitely there's not enough time to do that. All right, so a little definition here. F is of bounded variation on A to B. If the following is true, so there's different notation here. I just like to use this, but so TV for total variation, and this does define a norm. So we're saying the definition of this norm here is as follows. It's the supremum over all of these non-negative numbers. We're looking at the difference of my function, but some of the absolute value of the differences of the function, kind of seeing how it varies over all partitions of A to B. Right? So this is the usual Calc 1 partitions. So we have A is x0 all the way to xn is B. All right, so one trivial example of a function of bounded variation. So if this is monotone, then F has bounded variation or is of bounded variation. So what's the proof? Well, without loss of generality, assume F is non-decreasing or just increasing on A to B. Otherwise, just replace F with minus F, and replacing F with minus F has no effect here. I mean, it's just absolute value of this whole thing here, except the minus goes in front of the f of xj, and in front of the f xj minus 1 is a positive, but it's absolute value, so that doesn't have any effect. All right. Yeah, so given a partition, one thing I want to be clear, the supremum is, it's not like we fix an n and then look at this partition with n partition points, or n plus 1 partition points technically. We're just looking at all, it's like the Riemann sum, like we're kind of looking at all partitions for all different numbers of partition points. And then we're going to take the supremum of all that. Okay, so given some partition with however many elements. So this is really almost immediate. B. So yeah, there's no tricks here. Just look at the sum here. And yeah, you should kind of see what's going on. So this here is always bigger or equal to 0 because we are assuming that f is increasing. It doesn't have to be strictly increasing, but it is increasing. So this is going to be equal to f of xj minus f of x. And this is a telescoping sum. I'll just write a few of these out. J equals 1. F of x1 minus f of x0, which is a. X2 minus x1. I'll write more out here. You get the point here. I'll write the last two. F of xn minus 1. F of xn minus 2. And then f of xn is b. Yeah, so what cancels out? Well, if I had, well, let's just see what cancels out. So certainly this cancels out. F of x1, f of x1. F of x2's cancel out. If I had another term, the f of x3 would cancel out. If I had another term here, this would cancel out. Certainly these cancel out. So, well, of course, we're just, as usual, left with this one and then this one. Kind of trivially, this is going to be equal to f of a, f of b minus f of a. In fact, this whole set here, really what have we proved? This whole set here is equal to a singleton. It's f of b minus f of a. All these sums are f of b minus f of a if f is increasing. If it's decreasing, it's f of a minus f of b. So let's just dive into a prelim problem. So I'll end this video off with two prelim problems. This better be working or I'll really be pissed off. I think it is. Okay. So yeah, weird notation here. I don't really like this notation, but whatever. So you have a function on a to b, let t of a b be the total variation, exactly the same thing I had a second ago. I just like the norm notation because it is a norm, whatever. So it's almost like Fatou's lemma for the total variation norm. So it's a common theme to kind of do something like, try to do something like this. This is a really nice problem. It's actually quite easy if you think about it, but I mean, there's a lot of different ways you can think to try this using pointwise convergence. So we have Fn converges pointwise to F on A to B. Prove that total variation is less than or equal to lim m for the total variation. All right. So I think I will continue to use this norm notation, but yeah, I already forgot what prelim problem this was. January 2021, number 4. Let's see if I can remember that. Yeah. Okay, yeah, so how do we do this? Go back to black. So I think the easiest thing to do by far is so limits and soups don't really behave all that well in general. Especially if you all you know is pointwise convergence. It's So what am I trying to get at? Um Basically kind of um yeah, so I would say working with this here is that's tough. Like somehow using this as a starting point, because I mean, yeah, you have a lim inf, you have a soup, so it's lim inf of the soup, and somehow combine that with pointwise convergence. I would stay clear of that. Let's instead work with this. Okay, this is much simpler. We know what we need. We know what we need to do here, basically. So, what is the definition here? The definition here is a soup over all these sums. Right here. It's a soup over all these sums. So we can prove the lim inf is an upper bound, then soup is the least upper bound, and we're done. So that is the clear way to do this. Okay, so writing things down, what I want to do is prove that this lim inf of the variation norm, total variation norm rather, is an upper bound of all these sums, kind of defining the total variation for f. It's a soup of all these sums. So we want to prove that this is an upper bound. And instead of little n, I'll use big N. So yeah, this is my task. Right. A equals x0 less than x1, just like before. All right, so let's pick let's pick something. Let's pick one of these sums here. Okay. And again, the soup, the total variation norm of f is the soup over all these sums. So if I can do this, then I'm done. The total variation norm of f on a to b is it's the least upper bound. So as the least upper bound, it'll be less than or equal to this limit. All right. All right, so the key observation is that this is going to be equal to, because the finite sum, I can always interchange finite sums and limits. All right. And convergent limits are, well, equal to their lim infs. So lim inf is lim soup is the limit if the limit converges. I have on a slant here, but that's fine. Okay, well, so just a reminder, and I'll use I'll use M. So this, remember, is the soup over all these partitions. So I gotta remember to put n's here. And I'll use m here instead of n. Right, just like before, feel a little redundant in this proof here, but that's fine. Okay. Yeah, so the point is this sum here is one of these elements for particularly just some partition of A to B. So each one of these is less than or equal to the soup. I'll just write it like this. So for each n, this sum is less than or equal to the variation norm of Fn. Ignoring the lim m for a moment, each one of these sums is less than or equal to the variation norm of Fn. That's what I'm getting at here. So this is less than or equal to, and that finishes the proof. I mean, that's exactly, literally exactly what we wanted to prove. Okay. This, this lim inf is an upper bound for all of these sums here, no matter what kind of partition we have, no matter how many partition points we have. And since the soup is the least upper bound, I'm not going to write that, but we have exactly that. The soup, the total variation norm of F, is less than or equal to the lim inf. Okay, so it's probably not hard to imagine that you could have a really crazy non-continuous function that's not of bounded variation. So this is kind of an interesting prelim problem. What is this? June 2017, number 4. So give an example of a continuous function, hence uniformly continuous function on 0 to 1 that is not of bounded variation, and explain. I really don't like how it's worded. Don't explain, prove things. So any statement you make, prove it. Okay, so let's do that. Right. So yeah, June 2017, number 4. So let's say f of x is the following function: x sine 1 over x. If x, make this a little neater, smaller. I want to fit this in. And we want this to be continuous, so obviously the limit of the top here as x goes to 0 is 0, because this is always between -1 and 1, because it's sine 1 over x. So this has to be, excuse me, this has to be 0 if x equals 0. Now, what you could do, and actually originally recorded this video doing this, you could actually stick an x squared here, and this is going to be continuous. It's actually going to be differentiable on 0 to 1. You can check that very easily, and it's not going to be of bounded variation on 0 to 1. So you can actually come up with a differentiable function on 0 to 1 this, for example, that is not of bounded variation. You can actually stick any integer you want here to give you as many times differentiable as you would want. You can stick a k here if you want for a natural number k. But we'll keep things simple and just strictly stick with the prelim problem. Yeah, so f is continuous on 0 to 1. Nothing really there. You can just, it's continuous on this open 0, close 1, and directly you can check continuity at x equals 0. Okay, yeah, we're just going to go to the definition. We're going to cook up a partition of 0 to 1 with n plus 1 elements, where that sum is actually going to be roughly natural log of n. And well, natural log of n, as n goes to infinity, it blows up. So it's not going to be of bounded variation, my function. Okay, so let's say xj is 1 over pi j over 2. So you can even just maybe a little silly. So 2 over pi j, where j equals 1 to n. So let's do 1 to n minus 1. And to get a partition, set this to be 0, and this as it has to be 1. Okay, so yeah, let's just compute or estimate this sum here. This is not very subtle. I guess just thinking of this example is a little bit subtle if you haven't before. Right, so yeah, and if you had the x squareds here, you would literally just stick a square root here and everything. Basically, everything else I do from now on would work. But and again, the point with squareds here, this squared and this squared is that this function is interestingly differentiable on 0 to 1. Right. I guess I could ask that on a prelim, but I mean that'd be a little mean, I guess, and I'm just not a mean person. So. All right, so it's xj 2 over pi j, or am I? I'm really not a mean person, so. Yeah, that was a joke. Yeah, okay, and same thing, xj minus 1. So one thing I want to do, make my life a little easier, let's assume n is bigger than 3. So I want to eliminate the possibility we hit x0 and xn. Just make life a little easier. So this is bigger or equal to, just throw out these two terms just to save me time. And now I'll write out what f of xj is. It's, well, xj is 2 over pi over j, 2 over pi j, sine pi j over 2. So sine 1 over x gives me sine 1 over xj gives me sine pi j over 2. This is 2 over pi j minus 1 sine pi j minus 1 over 2. And now this is very straightforward. Let's see. So let's call this entire sum star. And let's see what's going on here. Right. All right, so this obviously equals plus or minus 1 if j odd, 0 if j even. So if j is 2, well, it's sine pi. If j is 4, it's sine 2 pi, etc., etc. If j is 1, sine pi over 2 is 1. If j is 3, sine 3 pi over 2 is minus 1. So yeah, it's 1 plus or minus 1 if j is odd, 0 if j is even. And this here is going to be the opposite. Of course, a little bit than that. Plus or minus 1 if j is even, and 0 if j is odd. Simply because j minus 1 is odd if j is even, and j minus 1 is even if j is odd. So, okay, so what's the point here? The point is if j is odd, then this is 0, or this is 1, and this is 0. If j is even, then this is 1 and this is 0. Right, so this here, right, so this here is going to equal 0. And the other is plus or minus 1, or this equals 0, and the other is plus or minus 1. The other being this one versus this one. Okay. So one of them is 0, the other one is plus or minus 1. So that means, and it goes back and forth, but that's fine. That means the absolute value without the sum is bigger or equal to 2 over pi j. 2 over pi j minus 1 is slightly larger. So we can't really say it's bigger or equal to that. But yeah, we can say star here because of this. This is bigger than j equals 1 to n. As I said a second ago, 2 over pi j. And this goes to infinity as n goes to infinity. So, yeah, this is not of bounded variation. Total variation, it's a soup over all possible sums like this over all possible partitions. This is one of them for each big N. So the soup is bigger or equal to each one of these for each big N. I believe if I remember correctly, this behaves kind of like natural log of j asymptotically. But certainly from calculus, it goes to infinity as n goes to infinity. Yeah, this is true for each n. This goes to infinity, so that implies that this is infinity. Right, so f is not of bounded variation. All right, so one more video on absolute continuity, and this is a really nice topic. We're just going to again kind of poke a little hole into, or take a little peek into the concept of absolute continuity. Very beautiful subject. There's a lot of stuff in it in the book, actually, if you're interested. It is definitely a more advanced topic. So yeah, we just touch it. And a whole lot of prelim problems on it, frankly, why we're doing it. But besides that, it is really beautiful mathematics. So, all right, so long, take care, and last video up tomorrow.